All right, folks. So this week we are doing inference for a single proportion. And as always, I sent you the R Markdown document. You need to download it onto your computer and upload it to RStudio Cloud. I'm going to assume that you've been able to do that, and then you're able to open it up. We're going to start off, like always, with our library tidyverse and library infer, and press the play button. And then we'll load in that same example data set that I've been using all semester. And let's make our lives easier. I'm gonna have us look at this variable self-employed or works for somebody. Let's just drop the NAs from that data set so we don't have to do that every single time. So right now I have 2,348 observations. And if I click the play button here, now I have 2,261 observations. So I dropped the rows where there were NAs for self-emp or works for somebody. So far, we've been doing inference using simulation methods. The last lab was about randomization, and the one before that was about the bootstrap. And now we're going to do inference using distributional approximations. So this week, we're going to be using the normal distribution, and next week, I think we're going to use the t-distribution. We're going to learn a lot about a bunch of theoretical distributions. But today, we're just thinking about a particular parameter and statistic, in this case, a single proportion. So we're going to approximate our sampling distribution using the standard normal distribution, but we'll need a formula to approximate the standard error. So these should be somewhat familiar from lecture, but here's how we do the standard error for one proportion in a hypothesis test. It's the square root of the null proportion times 1 minus the null proportion over n. And in a confidence interval, it's very similar, but instead of the null proportion, you use your point estimate, your best guess for the proportion, which is your p-hat, your sample proportion. So these formulas allow us to use the normal distribution as an approximation. But we can only use those formulas and the normal distribution overall if the conditions for inference are met. So what are those conditions? Essentially, we need n times p to be greater than 10, and we need n times 1 minus p to be greater than 10, or greater than or equal to 10. So those are our conditions. If we have really small sample sizes, then we can't do an approximation using the normal distribution. All right. So for this lab, we're going to think about the proportion of people who are self-employed, and we need to start with a sample proportion, otherwise known as a point estimate. So we need to find the proportion of people who are self-employed. So this has to do with a single categorical variable, because remember the variable self-emp or works for somebody, it just has two options. Let's scroll over and look at it. So it's either someone else if you work for someone else, or self-employed if you work for yourself. So what I'd like you to do is go back to, I think it was lab 2 when we did categorical variables, and see if you can remember how to compute the sample proportion. And I'd encourage you to pause the video now. Okay, I'm going to do it. I'm going to take my data set, and then with the pipe, percent greater than percent, I'm going to group by the variable that I'm interested in. In this case, self underscore emp underscore or underscore works for underscore somebody. And then at the end of that line, I'll put a pipe. And then I'm going to summarize n is equal to n paren. And if I just ran that much, and I could control enter here, this will tell me how many people were in each of those categories. But I actually want the proportion. So I'm going to put another pipe at the end of my summarize line, and I'm going to add a mutate here where I say prop is equal to n divided by the sum of n. All right, and then if I press my play button here, now I see that the proportion of people who say that they're self-employed, it's 10.3% about. So it's a little bit more than 10%, but is it significantly more than 10%? So that's the sort of thing that hypothesis testing can help us answer. And we could have done hypothesis testing using randomization if we wanted to do it without a distributional approximation, but we're going to do it using the normal distribution. So let's try out our hypothesis. So we want to know if the proportion of people who are self-employed is greater than 10%. So we need to write out our null and alternative hypotheses. So I could write them out in symbols like this. I always start by thinking about my alternative hypothesis. I'd like to know if p is greater than 0.1. So that's the sort of interesting thing that I'm secretly hoping will turn out to be true. And then I need to cover the rest of the possibilities in my null hypothesis. So that's the one that I usually write second. And this is the thing that we're secretly hoping will turn out not to be true, so that it would be equal to 0.1 or maybe less than 0.1. We could also write this out in sentences if we wanted to, saying that our null hypothesis, the true proportion of people who are self-employed is less than or equal to 10%, and our alternative hypothesis, the true proportion of self-employed people is greater than 10%. So either way is fine, in symbols or in words. And then we're just going to ask R to help us do a hypothesis test. So we're going to use this function prop_test. And the way that that works is you pipe some data in. So I'm going to start with my GSS data and then do a prop_test. I specify my response, just like I've been doing for other types of inference. And if I just ran it with this much here, let's Control Enter, it's going to give me a bunch of information. One of the things that it's going to tell me here is that the alternative is that it is two-sided, so that it's like a not equal in the alternative hypothesis. And that's not what we actually want. So we need to change our null hypothesis. Otherwise, the test is going to assume the null hypothesis is that p is equal to 0.5. So that's why I had these other arguments in there. So response is equal to self-emp or works for somebody, comma, alternative is greater, comma, p is equal to 0.1, because we had that 0.1 in our hypotheses. So if I hit the play button here, I get a bunch of information. Probably the most useful thing here is our p-value, 0.353. And that's the proportion of our normal distribution that is as extreme or more extreme than the z-score. We don't see the z-score here, but it's being computed for us behind the scenes by R. So R is finding the standard error using that formula that we talked about, and then it's doing the p hat minus p naught over the standard error to find a z-score, and then it's looking at that z-score in the context of the normal distribution, and then it's finding the p-value. So it just tells me the p-value at the end here. Our generic conclusion here, well, maybe just pause and think for a second about what you think our generic conclusion is. So the two possibilities for a generic conclusion are that we reject the null hypothesis or we fail to reject the null hypothesis. And in this case, we are going to fail to reject the null. And that's because our p-value, because 0.353 is greater than 0.05. That's our usual alpha level cutoff, 5%. So we have this big p-value, it's way bigger than 0.05, so we're going to fail to reject the null. And what does that mean in context? We do not have evidence to suggest that the true proportion of self-employed people is greater than 10%. We failed to reject our null. So that's one inferential task that we could do, hypothesis testing. The other inferential task that we might want to do is confidence intervals. And I always say that confidence intervals allow you to answer the question, what are some other reasonable values we could have observed? We saw that 10.3% of people are self-employed, but what are some other reasonable values for that percentage? And again, I could use prop_test to help me. So I don't have to specify all of the same things that I needed from before. I don't have that alternative and I don't have the p equal like I had when I was doing the test, but I do need to say conf_int equal true. And if I wanted to learn more about the prop_test function, I could do in my console prop_test. And then I would get some documentation about this tidy proportion test. I usually scroll down to the arguments because that will give me things like, okay, the alternative, it could be two-sided, greater or less. Conf_int is a logical value, meaning a true-false, for whether or not to report the confidence interval or not. So it is true by default, but ignored if p is specified. So that's why we didn't get one before. So let's just try running this code. We could click the play button. And here's the part of the code that we want to focus on. So the lower CI and the upper CI at this end. This p-value stuff over here now doesn't really mean anything because we haven't specified anything about a hypothesis test, so we can just ignore that part. But we want to look at these two numbers for the upper and lower CI. And then we might want to interpret that confidence interval. So I would probably say I am 95% confident that the true proportion of US adults who are self-employed is between, and then I'm just going to round some of these percentages. So I'll say 9% and 12%. So I don't know. You might round differently, 9.06% and 11.6%, but something like that. So it's between these two numbers. And then that could help me be more confident about making a statement about the proportion. Instead of just giving a point estimate of that 10.3%, I could say, well, I'm 95% confidence between 9% and 12%. So I think that is enough code for you to actually do the real lab. But I also included an appendix in here in case you wanted to see how you would do this whole set of inferential tasks by hand using R as a calculator. So for example, if we wanted to do the hypothesis test by hand, we would need to find the standard error. So we'd need to do this square root p0 1 minus p0 over n. And we could use R as a calculator. So my p0 value was 0.1, which means 1 minus 0.1 is 0.9. And my n was 2,261. So that would be my standard error. Then I could find a z-score, my observed minus my expected, or my statistic minus my null over the standard error, and my z-score is 0.475. And then I'd need to see how extreme that 0.475 was in the context of the normal distribution. So I have memorized that you need to be beyond 1.96 for a z-score in order to be significant. So I know that 0.475, that's closer into the middle, it's not going to be significant, but I could find the p-value using p-norm. So if I don't do 1 minus, I could just do p-norm 0.475. This is like everything to the left, so I need to do 1 minus, but I think that's the same p-value that we found when we used prop_test. And the reason why I need to do 1 minus the number is R is always thinking about the area that is to the left, and because we want to know to the right, we have to do 1 minus. I could also build like a crazy long data pipeline, GSS, then group by self-employed, then summarize n equal n, then mutate prop equal n divided by sum of n, total is equal to the sum of n, and then filter out. This is sort of a weird thing. I have to filter the data so it's just the self-employed people. I have to find the standard error by doing the square root of the proportion times 1 minus the proportion over the total. Then I need to find the z-score. Then I need to find the p-value. But I think that that comes out with basically the same p-value again here. So that would be a sort of a different way to do it by hand. And then I've got the same thing for the confidence interval. So we could try to find our standard error by hand, use R as a calculator, slightly different standard error, almost the same, but a little bit different. And then for the confidence interval, we'd need a critical z-value. Again, I have that memorized about the normal distribution. It's 1.96. But we could check using Q-norm. So if I do Q-norm of 0.975, sure enough, I get 1.96. And the reason why I do 0.975 is because, again, R is doing everything to the left. So if I think about my normal distribution, I want 95% in the middle. That means I want 2.5% in one tail, 2.5% in the other tail. So I'm looking for the line where 95% will be in the middle, which means 95% plus 2.5% or 97.5%. So that would give me my critical value, and then I could come up with my interval. This is, again, I think this is the same interval you got from the prop_test. I'm just showing you how to do it by hand. And then you could turn this into a totally long pipeline if you wanted to do it in a really tidy way. It's so long that it doesn't even want to all print out. But I think that this is the same kind of interval that you got with prop_test. So no need to do the by hand way for the real lab. That is just kind of appendix extra stuff in case you wanted to know what was going on behind the scenes. Prop_test should be enough to get you going on the real lab.